In this video, our main topic is the Fokker-Planck equation. This equation describes the probability density of a stochastic process evolve over time. In the last video, we looked at the stochastic differential equations. Those equations describe the evolution of a single random realization, one random path. We looked at the geometric Brownian motion. The solution of the stochastic differential equation will give us one global path. In general, this is known as the Ito process. And in the case of geometric Brownian motion, the path follows log normal distribution. So the main topic today is that we want to look at the evolution at the population level. So that is given by the Fokker-Planck equation, which tells us how does the probability density function change over time. So this is the equation that we will derive today. The solution of the Fokker-Planck equation gives us a probability density function at each time point t. What this means that if we have several stochastic processes, and we look at the snapshot at time t, then we'll have a distribution over the process value. The Fokker-Planck equation tells us how does this density function change over time. So if we look at this process at the time t plus delta t, the density function is going to change a little bit. So the change of this density function is exactly governed by the Fokker-Planck equation. The important thing to keep in mind is that this equation is not random, it's a deterministic process. This means that even at each individual path level, the process is random. But at the population level, the density function evolves as a deterministic process according to this PDE. That is the idea of the Fokker-Planck equation, which is something we'll derive in this video. The derivation of the Fokker-Planck equation will follow the same structure as the heat equation, which we derived in the first video. Okay, let's get started. So the first thing that we can do is that we can use the Chapman, we can write down the Chapman-Kolmogorov equation again as a starting point. And in this case, the stochastic process is given by an Ito process. So the Chapman-Kolmogorov equation is very intuitive. We're just saying that the probability can be broken down into a transition probability. So let me give you an intuitive example. So suppose we have a stock process. So it's just saying that at t plus delta t, if our stock price is $100, what this means that we just need to sum over all scenarios at time t. For example, the stock price equals to 80, equals to $90, or equals to $1,000. So basically, we just consider all scenarios, and in each of these scenarios, right, we'll have a transition probability to $100 at t plus delta t, and we just need to sum over those, right? So we just have a transition probability as this is $100 at t plus delta t, given by $y at t. So that is the transition probability. So it corresponds to this term here is a transition. And then we also need to multiply the probability at time t, right? So these are the probabilities of price y at time t. Then that is going to give us the price of x equals to $100 at time t plus delta t. So that is the idea of the Chapman-Kolmogorov equation. So now the main challenge is how can we compute the transition probability? So recall that in the case of the heat equation, right? In the heat equation, we can actually directly write out the transition probability. That is given by the Brownian motion. So recall heat equation. So our derivation from Brownian motion to heat equation. So the probability of x t plus delta t given y at time t equals to the density function of Gaussian. This is because the transition process is given by the Brownian motion. So basically dxt equals to dbt. But let me just reparameterize this a little bit. I'm just going to define the jump size, as z equals to x minus y. This is the jump size. We can replace this y with x minus z. And for the Gaussian, we can replace this with z squared. So see here that the key is that the transition probability does not depend on the position x. Regardless of where we make the jump, the transition probability is the same. But that is not the case for the general Ito process. So the reason is very intuitive, right? So if you just consider the stock price, so you can imagine that the jump, say that from $10 to $11, the probability of that, it is not equal to the probability, say we jump from $100 to $101. Even though the size of for this case is 1, right? We have z equals to $1, but the probability won't be the same, right? Because this has a 10% increase, whereas the second case only have 1% of the increase. So if the stock price follows geometric Brownian motion, it's definitely the second scenario is going to have a higher probability than the first one. So that is one of the main difference between the Ito process as a stochastic process versus just the Brownian motion. And we need to consider this during the derivation. But the structure follows the same, right? So if we recall that in the derivation of the heat equation, we just apply the Taylor expansion from which we can convert the integral into the moment of the stochastic process. So that structure still works, but we just need to be a little more careful about the Taylor expansion. That is the key. Okay, so now we are ready to derive the Fokker Planck. So let me just rewrite the Chapman Kolmogorov with respect to the jump set z. Okay, so this is the same equation, but we just need to sum over all possible jump sets z as the difference between the stock price at time t. So that we started with x minus z, then the stock price changed by z, so we can reach the stock price of x at time t plus delta t. So this is the same equation. And here I'm just using a different notation for the transition probability. So basically this equation, this is the transition probability. So that just equals to the probability of the process equals to z so equals to x at t plus delta t, condition on the process equals to x minus z at time t. So basically, if we think of this as a function, right, this function has two arguments. One is the starting position, and the other is the set z. Now, in order to perform the Taylor expansion, we need to consider the product of these two functions together. So in the case of heat equation, we only expanded the second probability here. We didn't, because the first probability is the same regardless of the starting position. But the challenge here is that the transition probability varies according to the starting position. So we need to include that in the Taylor expansion. Okay, so the idea is that we can just define the product of the two functions. Let's call that capital F. It has two arguments, so that equals to and here for the simplicity, I'm not going to write the time t because that is a parameter, because that can be considered as a fixed parameter for this function. We only consider x and z are variables. For the Taylor expansion, we're just going to expand with respect to the first parameter. We're going to expand that at point x. So basically, so we're just going to expand this to the second derivative. So notice that the first argument appear in both terms, right? So so that's just going to equals to and then if we just plug this back into the integral formula, right, we'll see this integral is over the jump set z. That is over the second parameter. So let me just copy this equation. So we'll have px t plus delta t equals to an integral and let me just copy this equation. And we'll integrate that over the jump set dz. Okay, so now we can just separate all the terms, right? So with the first term, we will have the integral of the transition probability. We can move the probability of x outside because that does not depend on z. Then for the second term, we'll have the integral and in our derivation of the heat equation, we directly convert this into the moment. Okay, so now let's take a look at these terms. The first term is easy because G is a transition probability. So that means this integral equals to 1. And then for the second term, you can actually move this derivative operator outside. And also you can move this px outside, right? And that's just going to give us something related to the first moment, to the expectation of the jump size. Then the same for the third term. You can move the derivative operator outside, and then we can move the probability px outside. Okay, so let's do that. The first term will reduce to p of x, and then we'll have the derivative operator act on px times the integral of we only keep the term related to z inside the integral, and then we'll move the derivative operators out, and then we'll have the px, the product between px times the integral plus the higher order terms. Okay, so now if we look at this integral here, right, what is this? This is just the moment of the jump size z. So this is just the expectation of z under the transition distribution. For the next one, right, we'll have the second moment. We'll just have the first and second moment for z under the transition probability. So this is very nice, right? Because we're just steps away. According to the Ito process, over a small delta t, we can directly obtain those, the first and second moment. So this is the Ito process formula that we use. So the property is that as the time interval delta t goes to 0, then the delta xt is approximately Gaussian distributed with mean and variance. And here you can directly swap this out with z, right? So this implies that the first moment of z equals to mu times delta t. And then the second moment of z equals to the variance of z plus the first moment square. So that equals to sigma square delta t plus mu square delta t square. And then because delta t is very small, right? So this delta t square simply goes to 0. So we'll just have the sigma square delta t. And then for Gaussian distribution, all the higher orders, right? So let's say z to the d's will all goes to 0 as delta t goes to 0. So that's the property of the Gaussian distribution. And by applying this property, we can finish off this derivation. So on the left-hand side, we'll have probability of x at t plus delta t equals to the probability of x at t minus the first derivative Okay, let me just add the time parameter back to make things clear. And then we'll have the first moment equals to mu times delta t. Okay, let me just spell out the mu, right? To indicate this is not a constant. We'll have mu, the parameter being t and x. And then we'll have times delta t plus a half times the second derivative, density multiplied by the second moment, which is sigma square times delta t, and the higher order term goes to 0. Okay, so now all we need to do is just to move this probability to the other side, and then I will divide this equation by delta t. So so what we get is that we'll have px plus delta t minus px t over delta t equals to minus plus the second derivative So if you look at this left-hand side here, right, this is just a partial derivative as delta t goes to 0. So I'm just going to replace this with a partial derivative. And that is the Fokker-Planck equation. So basically, this derivation is quite similar to the derivation for the heat equation as we did in the first video, except that we have to consider the jump depending on the starting position. And in fact, we can see that the heat equation is a special case. It is basically the case where the mu equals to 0 and sigma equals to 1. Right, then if we just plug it into the Fokker-Planck, we'll have the partial p with partial t equals to, the first term just goes away completely. And then all we left is the second term, the half times the second derivative act on the density p. So this is the heat equation that we derived before. Okay, let's look at another example. Let's look at the geometric Brownian motion. So in the case of geometric Brownian motion, so we'll have the mu equals to a constant mu times x, and then we'll have sigma equals to sigma times x. Okay, so this notation is a little bit confusing, right? So the mu sigma here, these are the constant. Okay, so now we can just plug it into the Fokker-Planck equation. We'll have the partial p with partial t equals to minus the first derivative of mu times p times x plus a half second derivative times sigma square x square times p. So this is the density evolution that we use to model the stock price. So I'm not going to solve these equations in here, but if you solve it, we'll find that the p It's just the density for it's just gonna be the probability density function for the log normal. And in the case of the heat equation, right, the P, if we solve it, P will be the probability density function of normal. However, in the general case of the Fokker-Planck equation, it can be quite challenging to solve because these parameters, the mu and sigma, depends on the position of the process. And another interesting thing is that the Fokker-Planck equation actually belongs to a family of PDE called the parabolic PDE. So basically, the parabolic PDE has the following form as the partial with respect to t equals to a, basically some coefficient times the second partial derivative with respect to x plus another coefficient times the first derivative plus another constant times u. And we have one more condition to say that the coefficient with the second partial derivative is greater than 0. And if we look at the case for the geometric Brownian motion, that is satisfied, right? For the heat equation, it's also satisfied. And you'll see that in the Fokker-Planck equation, right, even though this coefficient is kind of changing, but it's satisfied to be positive. So basically, the heat equation is the simplest example for the parabolic PDE. And the parabolic PDE can follow the same intuition to describe a diffusion process over time. Okay, so that's pretty much about this video. We look at the Fokker-Planck equation, and we see that, so this is the rule of how the probability density change over time. So we started with the stochastic differential equation, the Ito process, and derived the deterministic evolution for the density function. In the next video, we'll look at the Kolmogorov backward equation. So that is the engine behind the Black-Scholes equation for option pricing. It is another deterministic PDE that describing how we can trace the expectation of the stochastic process over time.